Hello everyone, and welcome to World Science Festival Brisbane 2021. It's so great to have you here. I don't know about you guys, but I'm sick to death of Zoom and online interaction. So today is extra special because we have got an actual real live scientist, and not just any old scientist. We've got a paleontologist. Is anyone here a fan of, I don't know, dinosaurs? You don't sound like much of a fan to me. Is anyone here a fan of dinosaurs? Is anyone here wearing a dinosaur t-shirt? Come on, I saw you walk in. You're wearing one right in the front row, looking around to see who else is. Yes, we're loving it here. So today is all about ancient sea monsters, so mostly about dinosaurs of what was then the deep. I'm obviously not the person who can tell you about that because I'm a biochemist, so my knowledge of dinosaurs is about 50 years out of date and a distant memory. Before we get going, I start today's session by acknowledging the First Peoples, the traditional custodians of the land on which this festival is being presented. And I also recognise and pay my respects to the first scientists of this land, because increasingly in many scientific fields, we're recognising the important contribution that First Nations science makes to contemporary scientific discovery. So it's so great to have you here to learn about what kinds of amazing, not just dinosaurs, but ancient sea reptiles, crazy things like, has anyone heard of an ichthyosaur? I just heard of them this morning. They seem pretty cool. What about, has anyone heard of do you know what came in after the ichthyosaurs went extinct? Yeah? Yes? Plesiosaurs. Okay, I feel like if our expert, Espen Knutsen, can't cover all our questions, we've got someone here who can answer them for us right here and right now. Would you please give a very warm welcome to our special guest speaker, Dr Espen Knutsen. So Espen is a paleontologist at Queensland Museum. He actually set up the Ancient Sea Monsters exhibition that you've all got included in your ticket today. So any questions about that, he's totally your man. And today Espen's going to be telling us all about how he's going all around Australia, kind of like Indiana Jones, but way cooler, going all around Australia looking for traces of fossils, ancient sea fossils, that will help fill in the gaps of the records from the past, 250 million years, whatever, So that's the work that Espen's doing. You've got some great photos, you've got some great movies, and I'm gonna be pretty quiet, but I'm gonna have to say if any questions come to me, I'm just gonna jump in the middle because I'm extremely curious. But then we're going to hand over to your questions later on, okay? So my name's Bernie Hobbs. I'm a science communicator and really rapt to be here with you today. But if you can hold your questions off to the end and just let me get a go at it, from a very large family, very competitive, need to talk a lot, okay? So if you can just let me have my go now, and then it's all up to you later, all right? And then you get to go and see the exhibition yourself. But that's enough from me. Give it up for Dr Espen Knutsen.
Thank you. So firstly, when we all think about reptiles, what comes often to mind is snakes or lizards and turtles and crocodiles, which is how we see most reptiles today. And as we know, reptiles today are cold-blooded, so they lie around and they soak up the sun to warm up in the morning so they can become active. But reptiles are so much more than that, not just in the past, but also today. Birds are reptiles, evolving from meat-eating two-legged dinosaurs about 150 million years ago to become one of the most species-rich four-limbed vertebrates that we have alive today, with over 10,000 species of birds. And birds aren't cold-blooded at all. They have a body temperature well over around 40 degrees and don't need to sit and soak in the sun to get active in the morning. And similarly, we had a whole heap of different reptiles in the past as well. So in the last 340 million years, we've had reptiles that fly, we have reptiles that live in the ocean, and we have reptiles that live very similar to how plant-eating mammals live today, so grazing reptiles even. So I've shown you some of the reptiles up here and how they relate to one another. And as you'll see, we've got a lot of reptiles that aren't related to lizards or snakes, and a lot of reptiles that aren't related to dinosaurs as well. So for instance, pterosaurs, that are the giant flying reptiles of the age of dinosaurs, they weren't dinosaurs at all, but a sister group of dinosaurs. And similarly, also the marine reptiles that we have up here are also sister groups to dinosaurs. So they're not really any more closely related to dinosaurs than we are to dogs, really, in that sense. So we try and discourage people from calling, at least us marine reptile experts, to try and discourage people from calling these Plesiosaurus Nicothesaurus for marine dinosaurs, because they're actually very distantly related. So if we go back to when the first reptiles evolved around 340 million years ago, the world was a very different place, dominated by amphibians mainly and large fishes. And these reptiles and also the amphibians evolved from tetrapods or four-limbed vertebrates that have evolved from fish-like ancestors much earlier. And these fish-like ancestors evolved into, like I said, amphibians and reptiles. But as you know from today as well, amphibians have these sort of gelatinous type eggs that don't really thrive on land. They just dry out and the egg dies. So they have to be laid in moist environment or in water. Whereas the ancestors of reptiles and stem or early mammals, their eggs actually had a shell that prevented the egg from drying out. And they also have a special skin that prevents a lot of evaporation of water from the body. So these things together made reptiles and stem mammals a lot better adapted to live a life on land than these early amphibians. So while amphibians and large fish were sort of dominating in the lakes and in the rivers and in the oceans, stem mammals and reptiles were dominating or ruling the land. But then, about 252 million years ago, things changed drastically. So we had a large extinction event with more than 95% of all life going extinct. And one of these events that happened at that time, that led up to this, was huge volcanic eruptions in what is now Siberia. And all these volcanic eruptions led to global warming due to all the CO2 being released, and the global warming led to ocean anoxia and also ocean acidification, which is quite relevant today. And this led to the extinction of a lot of the animals and plants that fed the animals that lived in the ocean and also on land, leading to an ecosystem collapse and extinction of a lot of these dominating apex predators in both the ocean and on the land. And the aftermath of this left the planet going from a sort of humid, warmish place with swamps that we now see as coal beds in the Permian period, so about 260 million to 252 million years ago, to a really dry, arid climate generally, with high seasonal variation in the weather. And we can see this in the rock record as we go from the Permian through to the Triassic period, from about 260 to 250 million years ago. We see a lot of coal-forming beds that were these swampy, humid areas, to arid, sunburnt sediment like these red beds that we call them here, that we can see, for instance, here in central Queensland, from this locality. That used to be a vast river plain where we had amphibians and reptiles living, and even possibly the early ancestors of dinosaurs. So a very different place where a lot of these apex predatory fish and amphibians that dominated the oceans and the lakes and river systems in the Permian had vanished, opening up opportunities for reptiles and stem mammals to take their places. And also a climate that much favoured animals that had a better chance of surviving on land and out of water. So this is sort of what the Earth looked like back in the early Triassic period. We had, because of the global warming, there was also a lot of ice melting that raised the sea levels and inundated a lot of the land. That created these vast, shallow sea areas. And because we had hardly any of these apex predatory amphibians or the large fish remaining after the end Permian extinction, and we had, in combination with these vast shallow seas, it was like an evolutionary nursery for these reptiles and possibly also stem mammals that wanted to try out, if you like, life in the water and evolve into water-living or aquatic tetrapods. And this is the time period in the next 15 million years or so after the end Permian extinction. So from around 250 to 230 or something million years ago is when we see all these marine reptiles evolve that become dominant in the rest of the Mesozoic era. So from 252 to 66 million years ago, when also the dinosaurs were living on land. So going from a life on land to a life in the water requires a lot of different adaptations. So animals even today that have adapted from a land-living ancestor to a life in the ocean look very different in many ways to their land-living ancestors. And it's got mainly fundamentally to do with the way you move, because of moving through water is a very different medium than moving through air. It's a lot more resistance, and they also don't walk on the ocean floor or the bottom of the lake or in the river, but they swim through the medium. So they need a way to do that. So the way they often do that is they either elongate or flatten their limbs or their tails and use that for propulsion through the water. But they also got to evolve other ways, so holding your breath and that sort of thing, and also different ways of feeding. And a lot of these adaptations, like the swimming, makes them more and more efficient feeders and foragers, which makes them adapt more and more into an aquatic sort of lifestyle and body shape. And we see the same with the ancient marine reptiles. We have their fossil record, and we can see from the earlier ones that are the shallow sea varieties where they look a bit like sea otters, to the more fully formed marine types where they look a bit more dolphin shaped, or they have large paddles, flat flippers like we see in sea turtles today. But also, as with sea turtles and sea lions and seals, they got up on land to give birth. So they're not, in a sense, fully marine because they actually still have a tie to the land. Whereas a lot of the marine reptiles and whales today as well, they actually give birth in the water, so they never have to go up on land for any reason whatsoever. And we know that a lot of these ancient marine reptiles did that as well from their fossils. And we have Plesiosaurs, for instance, that have little juveniles or embryos preserved inside their body cavity. And we even have Ichthyosaurs, where there's heaps of embryos or juveniles inside, and also even ones that are on the way to being born as well, on the way out.
Sorry, Espen. I mean,
yeah.
That is spectacular, but how can you be sure that those tiny little things are not just, I don't know, how can you be sure that they're embryos?
That they weren't been eaten.
Exactly. Some peas that they had for dinner.
Yeah, that's a very good question. And one of the ways we can do that is we can look at the bones, and if the bone had been inside the stomach, you can see acid marks on the bones themselves. So you can see how they've been corroded or etched away from these stomach acids. And none of these bones of these little ones actually show that at all. And the fact that this also is sort of tail first and head last is typical of what we see in fully marine animals even today. And the reason why you want to come tail first is because if you come head first and you get stuck and you're an air-breathing animal, you run the risk of drowning before you're fully born.
Sorry, Espen. Is that's being born?
Yeah, that's essentially being born.
Sorry, I missed that.
So it's probably gotten stuck on the way out, which also happens to animals today, obviously. So coming head last allows the embryo or the newborn to come out safely, and then first thing it does is to swim straight up and take its first breath of air, just like human babies do as well, except we're not in the water. So these dominant ancient marine reptiles that we see are the Plesiosaurs, which are these four-flippered things that look like that, and they sort of evolved two extreme body shapes. This is one of them with a really long neck and a tiny head on the end, and the other one is the ones with the really giant heads and a much shorter neck called the Plesiosaurs.
Okay, can I just ask, you're sure that you haven't put together two mismatched dinosaurs to get that top one?
Yeah, so we sometimes used to say that it looks a bit like you shoved a snake through a turtle shell, except it doesn't have a... Yeah. So it looks quite different, very different from anything you have today, which is one of those things that sort of puzzles us as paleontologists, because we don't have anything with four flippers that swim like Plesiosaurs would have. Because looking at their joints, we can see that they would have used all 4 flippers at the same time for swimming, whereas turtles really just use their front flippers and they just use their rear flippers as a rudder. So these were one of the kinds that evolved in the Triassic and lived through the Jurassic to the end of the Cretaceous period. And the other dominating one are the Ichthyosaurs that look kind of dolphin-shaped as you get into the Jurassic and Cretaceous period, but prior to that they look a bit more similar to this mosasaur, which is actually a relative of snakes and goannas. And Ichthyosaurs, they became highly specialized in the Cretaceous period, which probably led to their demise because in the mid-Cretaceous period we had again a climatic upheaval and global warming that led to a ecosystem collapse in the ocean, and these guys, feeding on very few types of organisms, met their demise and actually went extinct about 90 million years ago. So it didn't last till the end of the Cretaceous when the dinosaurs were around, but went extinct sort of midway there. And were replaced by these mosasaurs that are these goanna-like things that lived in the water. And these could be fairly giant things as well, well up to 15 metres. Same as these plesiosaurs that we find here in Queensland, anywhere between 10 and 12 metres as well. So these guys here, the plesiosaurs and ichthyosaurs, the mosasaurs, were around right till the end of the Cretaceous period when the dinosaurs went extinct, when the asteroid hit Earth in the Yucatan Peninsula in Mexico, just outside Mexico, and sort of killed off about 76% of all animals, all life. So that's sort of how the marine reptiles evolved and what they are. We learned that they're not dinosaurs. We learned they evolved firstly from an aquatic or marine ancestor via amphibians and tetrapods into reptiles living on land for tens of millions of years, and then evolving back into a form that lived in the water. But now going the other way, having to, instead of learning how to breathe in the air from an aquatic ancestor, having to learn how to live in the water while being an air-breathing organism. So I'll show you a bit of how we go about finding the fossils of these things. So I get that question a lot. How do you find these fossils? Do you just wander out and hope for the best? Or how does that work? So what we do is we have these things called geological maps that really helps us paleontologists to firstly pinpoint where we should be looking. So what we know is that ancient marine reptiles lived in a marine element, so they lived in the ocean. So we want to look for sediments that were deposited in the ocean, so they could be sandstones or siltstones or mudstones. And then we can look at the other fossils that we can find there. So there might be clams, there might be starfish, there might be a fish, or other things that suggest to us that this was a marine environment. So looking at that, we can determine which type of rocks we want to look at. But then we also want to make sure we're looking at the right age of the rocks. So we know that Plesiosaurs and Ichthyosaurs, for instance, lived in the Mesozoic era, so between 252 to 66 million years ago. So we want to make sure we go to the rocks that are of that age. And we can use these geological maps. So geologists and other scientists have been out, walked the land or flown over in a helicopter, and they've mapped all these different types of rocks. What is sandstone, what is siltstone, what is mudstone, and so on. And then, if we're lucky, these rocks have also been dated. So it'll tell us what age they are. So if we go to the geological map, we want to find a plesiosaur from the Cretaceous period. We go, okay, that's the Cretaceous period here in green. We know that all this area here in green has Cretaceous rock on it. And then we might want to go on something like Google Earth or an aerial photo, and we want to see where is there a whole heap of vegetation or where is there actual outcrop. Because we are dependent on when we go out that we can actually see the bones on the ground. If it's only got even like a millimetre of dirt over the top of it, we can't see it and we have no idea it's there. So then it's just a matter of going out, looking around on the ground and trying to find these pieces of whatever might have been around at the time. And one of these places we go is Western Queensland, that sometimes looks a little bit like this, vast open plains covered in this black soil. And sometimes the black soil will churn over time because of the wet and dry cycles, so it swells and contracts and it churns anything from the rock that's sitting 2 meters underneath, might churn these big blocks up to the surface, which is how we can find some of these bones. Other places we go to, we have actual rock outcrops, so there might be a hillside and you can see the layers of rock sort of in the side of the hill. So that's the preference, because then we can see exactly where the fossil is coming from inside the rock and we also have a much fresher fossil that we can excavate. So once we've gone around and we sort of look for pieces that might have tumbled down the side of the hill, because that's what happens when a fossil starts becoming exposed on the surface, little bits will sort of break off and roll down the hill, often in a triangular shaped pattern. We can then walk around and we go, there's a piece, there's a piece, there's a piece, and we follow it up the hill until we find exactly where in the side of the hill it's coming from. And often the pieces are much more visible on the surface than the actual fossil itself, which is this little line here. So it's relatively easy to find these pieces, but very hard to find where the fossil actually is coming from. So when we start looking, we'll start at the bottom of the hill and work our way up, rather than the top and work our way down.
So, sorry, Espen, you would have seen those bottom ones just hanging around there, and then have you uncovered the fossil, or it was just sitting there exposed?
So that was sitting there just like that. But sometimes what you'll get is different types of minerals as well that can come out. It can be gypsum or calcium or something like that comes out that looks similar to that. So it's hard to go to all of the ones that look sort of white. It's better to go and you find these pieces. So we've brought those up from the bottom of the hill, just carried them with us. They weren't lying like that.
Okay.
Yeah.
Because I was going to say your job is a lot easier than I thought.
So there's been about 10 of us walking on a line, zigzag line up the hill, sort of on all fours. And sometimes the fragments are very tiny as you get, especially as you get close to the fossil itself. So you've got to go right down there, right on all fours, and just have the ground right there and just sort of scour around and try and see what you can find. So that's just part of the process to actually find the fossil itself, and you can go for days, weeks. I've been out trips where for 2 weeks at a time where we've found nothing. And some places it's easy to find them, like this place here where I used to work in the Arctic is easy. You can walk around for an hour and find 2, 3, 4 skeletons. And we collected about 40 of them in about 8 years, but there's still probably another 100 out there that we've mapped so far. If you go other places, some places here in Queensland, you can find Ichthyosaurs quite easily. Some of the locals call them for roadkill, because they'll inevitably sometimes, we're going to dig a trench, or we're going to grade this road, or look, there was an Ichthyosaur right under the grader.
Wow.
So that happens. And but you can also go out there and you can find nothing as well, or you can find bits and pieces of animals. So depending on what sort of environment they'll be found in, for instance, this is a black shale, which is a really calm environment at the bottom of a deep sea. So not many currents or any scavengers that can move the bones around. So if the whole animal settles down on the bottom there, it's likely to be preserved as a whole animal. Whereas here in Queensland, we had a shallow sea, and I'll show you in a minute, that covered a lot of inland Queensland. And the shallow sea is about 50 metres deep, so you have a lot more current going through and a lot more chance of scavengers sort of moving bones around. So you might find bits of an animal, but not a whole one. And here's another one. So once we've found the layer that the skeleton is in, we want to try and expose that. So if it's on the side of a hill, we want to have to try and dig away at all the rock that's sort of sitting on top of it. So we do that with shovels and picks and all that sort of stuff first, to sort of, as quickly as we can, work our way down till about this far above the skeleton. And then we start getting the fine tools out, the brushes and the trowels and the little picks and all that sort of stuff, to slowly uncover the extent of the whole skeleton of what is there. So this is a paddle of a plesiosaur. That's 145 million years old. And it's got this blue tinge to it because the calcium phosphate, or the apatite in the bones, reacted with iron in the rock and created a mineral called vivianite, which turns blue like that. Once we've exposed the extent of the whole skeleton, we've got to document absolutely everything about the skeleton before we extract it from the ground. So what bones are there, where are they, how are they oriented, and what type of rock is it preserved in? Are there any other fossils surrounding the specimen or in relation to the specimen? For instance, here we've got an ammonite. And what might that mean for the environment that the skeleton was preserved in? Or what might the orientation or preservation of the bone tell us about what happened to the animal after it died? So for instance, the bones might be scattered, which is called disarticulated, which suggests to us that it might have been sitting on the bottom for a while before it got covered by sediment, and either current or scavengers might have moved the bones around from their original position. And you can find bite marks on teeth on bones sometimes, which tells us that they were being gnawed on by other animals, or even borings from worms or bivalves or other things that live in the ocean.
And can you tell, Espen, if you see bite marks, can you tell if they were bite marks after they were dead or if that might have been the cause of death?
Yes, so for instance, if it looks like it's been healed and it was likely there for a while the animal was still alive. Other times you can see that there's typical like gnaw marks from especially the front teeth of different animals. And that suggests to us they were sitting on the surface for a while it was dead, so it was a carrion or sitting just on the ground, for instance, if we're talking about land-living animals. And the animals or the predator or the scavenger would have come and sort of scraped the meat off the bone. You can see those tooth marks on there. So all these things, all these notes we take tell us something about the animals, what happened to the animal after it died and between it died until we found it. And that's called the Tauponomy of the fossil. So that's a large study in itself and very important step. So when we find a fossil, we don't want to just extract it, we want to know everything we can possibly about it. And it's also very important for, especially for these larger animals, because we can't really make one big plaster jacket, as I'll show you in a second, to collect the whole 8-meter long plesiosaur. So we've got to cut it up into pieces that are manageable to bring back to the museum for us. So often we do a bit of spinal surgery, so we're taking one vertebra out of the neck of this one here to make it into a bit more of a manageable piece. So then we'll number that chunk. We'll label it in the field drawing that we made, and we'll label the bone as well and when we wrap it up, so we'll know exactly where it was, where it belongs. So when we come back to the museum, we can put it back in its exact position after we've taken it out and reassembled it in the museum. So the process, once we've uncovered it, documented everything, is we've got to cover it in wet toilet paper first, which might seem funny, but it's because we can't put the plaster straight on the bone because it'll stick to the plaster and we'll never get it off again. So we put this layer of wet toilet paper in between to release the plaster from the bone. And then we use wet hessian or burlap, if there are any Americans here, and soak it in plaster, and then we start wrapping the top and the sides of the fossil and the rock. And what we want to try and do is create a cocoon or half cocoon that sort of holds in the rock around the fossil. So when we've undercut it like that on all sides and wrapped more plaster and plastered hessian around, once it's set, it'll actually hold everything in, and we can flip it all around and expose the underside without everything just pouring out from inside the plaster jacket. And that's the process of trying to actually extract it from the side of the hill. So sometimes we have little jackets. If we have the car far away, then we need to carry quite far. Other times we have big jackets like this one here that weighs probably at least a couple of 100 kilos, and we need a lot of people to help out to flip these things. And you also need a helicopter or a truck nearby to be able to bring it back to the museum. And then once we've flipped it, like we saw here, we've got to dig out the excess rock, because often when we make this pedestal and of the plaster jacket, we take a lot of extra rock just to make sure that it's all going to hold in when we flip it around. So we want to get rid of all that excess rock because we don't want to bring more rock back to the museum than we have to. So we start essentially excavating it on this side as well. So we just get our trowels and our brushes and we start digging out all the rock down to the fossil on that side too. And then we do the same process with the wet toilet paper down and the Plesiosaurus hessian until we've got a full cocoon containing the rock and the fossil inside, and we can now stick that in the back of a truck and carry it or transport it safely back to the museum. And in the museum we do the prep work. We extract the rest of the skeleton from the rock, and we document it as well. And one of these new ways of documenting skeletons these days, or fossils these days, is something called photogrammetry. So you can use laser scanning as well to make a 3D model, but if you have a camera, any camera will do, even a phone camera, you can take a whole heap of series of overlapping photos of a fossil or whatever it might be, and you can put it into so-called photogrammetry software, and we'll look at all the pixels, overlapping pixels between the images, and it'll make a 3D model out of that. So this skeleton here is a plesiosaur that's on display in Boulia, which is about a 10-hour drive one way from Townsville, where I'm located. So instead of having to drive 10 hours back and forth every time I want to see something or confirm something about the skeleton, I can just look at the 3D model of this 5-meter plesiosaur on my computer screen and get all the data that I need. And I can also print it in 3D, obviously, but I can also send this 3D model to a colleague of mine, for instance, that might be in a completely different country, and we want to confirm something on a skeleton, I can send him this, look at this, what do you think, rather than him coming to Australia and looking at the specimen. And I can also more easily share all this information with you guys, as you will see in the Sea Monsters exhibition upstairs when you go there after. And we can also do this for whole localities as well. So sometimes we'll have localities, there might be dinosaur footprint trackway that's 20 meters long. We can't collect that and bring it back to the museum. So using these 3D models, we can use drones or phones. We can generate a high resolution 3D representation of this whole trackway, or even localities like this, and we can easily map out the fossil occurrences. That gives us a better understanding of how fossils occur in a certain area. So this is a very powerful tool that we now have to use for both scientific purposes and also for scientific outreach, which is really handy. So what we've got here is this Triassic locality that I showed you earlier, where these ancient reptiles and amphibians were living. And I've plotted on all the fossil localities on here, and you can see easily where the fossils actually occur on this hillside.
And sorry, did you say, Espen, this is in central Queensland?
Yeah, and this is in central Queensland, this one here, and it's probably one of the most important fossil localities for this time period anywhere in the world. So what we want to try and do is use these data. We'll do it every time we go out. We'll make another 3D model, and you can compare these 3D models, and you can see how is the erosion going in this place, and how quickly is it eroding, where is it eroding more, and so on. And we can use that to plan ahead where to look for one, but also how we might preserve this area for the future as well.
Hang on a minute, I think I said I'm asking. I wanted to ask what was the difference between the yellow and the red, Espen? That was something that's been on my mind.
Yeah, so that was more for my benefit, because the yellow means that there's one specimen there, and the red just means that there's more than one. So some of those places you'll have one skeleton cropping out from a bank of what used to be a bank of a river, in a sandy river or something like that. Other places you might have a bed of mudstone where there's several skeletons preserved in what we call a bone bed, where you can dig out chunks of this, and there might be scattered bones of all different types of animals all jumbled up together. So there's quite different ways, especially in one river system. There's a lot of different types of environments that fossils can be preserved in. It could be a bend in a river, it could be a straight flow, it could be an overbank, or it could be a billabong. It could be a lot of different things that have different depositional preservation potentials. If we go back to the marine reptiles, here in Queensland, about 110 million years ago, we had an inland sea called the Aeromangosaurus Sea. So if you go to inland Queensland, as I showed you before, we can find the fossils of both marine reptiles like Ichthyosaurs and Plesiosaurs, but also turtles and crocodiles and fish and clams. And one of these plesiosaurs that we find here is called Aeromangosaurus, and that's one of these really long-necked plesiosaurs. And what happens a lot of the time with especially marine animals, and you see that today as well with whales, is that they'll die, then they'll sink to the bottom. If the ocean isn't very deep, they'll start floating up again. And the reason for that is because as they die and start decomposing the inside, it creates a lot of gases, so they sort of bloat up, and they float around like a little floaty toy on the ocean. And that's what we call the so-called bloat and float procedure. And what happens with these really long neck things is that they're sort of dangling with the belly up, these really long necks sort of hanging into the water with the little head on the end. And that is either a really tasty treat for a scavenger, or it might be one of the first things that sort of rots off and gets dropped off somewhere, while the body keeps floating around for weeks maybe at a time, or afterwards, before that sinks to the bottom and gets preserved. So what happens with these really long neck ones is that when we find them in the field, often we can find just the head with little or no part of the body at all, or we find just the body or part of the body. So we've got one head of these long neck plesiosaurs from here in Australia, and that's got the name Aeromangosaurus, but we've got plenty of bodies with no head at all, and not really any overlapping material between them. So we don't know what body actually goes with his head. But we know from the bodies there are at least 2 different species of plesiosaurs, long-necked plesiosaurs here, but we can't really make another species name until we know which of these bodies go with that head. So that's one of the processes that we are going through now. We're trying to go out there and find new localities and find new skeletons that might have this overlapping material that can sort out this problem for us.
If you can hold on just for a minute, we'll have questions at the end. Thanks.
So one of these new localities is in Western Queensland near a place called Prairie. There was one skeleton found here in the past, and that was donated to the Queensland Museum in about 1894. And we went out there in July last year for a little scouting trip, for a field trip for our paleo students up in Townsville, and we found a plesiosaur on the side of the hill.
Wow.
So we took the students out a few months later in September, and we collected that specimen. And it didn't have a head, unfortunately, but it is a brilliant locality to go out and find fossils from this time period, because we got kilometers of outcrop of this type of rock, and certainly has the potential for preserving these things. So we're going to go out there, keep going out there and collecting more and more, or prospecting for more and more, and hopefully we'll be collecting things as well. So with that, I'd like to say thank you for coming.
Hey everyone, let's give it up for Dr Espen Knutsen.